Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language video series, where today we're going to talk about multiplying mixed numbers. And I think this is going to be a nice place. It's come up before, where students memorize a certain rule that works in one situation. They want to use that same rule in another situation, but it doesn't work there. Where did that happen previously? Well, one place was the difference between multiplying fractions and adding them. For multiplying fractions, we saw that all we had to do was multiply the two numerators to get the numerator of the product and multiply the two denominators to get the denominator of the product. Okay? But when we added, if we added the numerators and added the denominators, that's where we saw we got the weighted average, not the sum. Okay? Two different things. The sum of two fractions one way, the weighted average the other way. The weighted average was wrong because it didn't give us the right answer to such problems as 30 minutes plus 20 minutes, where we wanted the answer to be 50 minutes because we knew that was the answer. So a half hour plus a third of an hour had to be 5/6 of an hour, etc. Same thing is going to happen here. Watch. Suppose a student is asked to add 4.5 plus 2.5. The usual way to do it again is they write it in vertical form, and they say, okay, I'll add the two whole numbers. 4 plus 2 is 7. 4 plus 2 is 6. A half plus a half is 1. 6 plus 1 is 7, and that's the right answer. Now they're given 4.5 times 2.5. And it worked here, so why not here? I'll multiply the two whole numbers. 2 times 4 gives me 8. A half times a half, which means the same as a half of a half, is 1/4. The answer is 8 1/4. Here's another thing about math. If you develop your number sense, even if you don't know what the right answer is, there will be times when you know that an answer that you've got is the wrong answer. For example, how can I show that 8 1/4 can't be the right answer? Well, 2 times 4.5, or 4.5 times 2, either way, 2 times 4.5 means 4.5 plus 4.5. 4.5 plus 4.5 by the rule for adding is 9. If it was money, $4.50 plus $4.50 is $9. 2.5 times 4.5 is certainly more than 2 times 4.5, because 2.5 is more than 2. So whatever the right answer is, it has to be more than 9. See, in other words, 4.5 times 2 is 9, and 4.5 times 2.5 is greater than 4.5 times 2, which is 9. So again, I don't know what the right answer is. Well, I know something about it. It has to be bigger than 9. So how can 8 1/4 possibly be the right answer? So what happened here? Where did the student go wrong? Why could they do it here, but they couldn't do it here? Well, let's expand things, and maybe we can see. Another name for 4.5 is 4 plus a half. Another name for 2.5 is 2 plus a half. So it's 4 plus a half plus 2 plus a half. Remember, addition is associative and commutative. I can juggle these around any way I want. I can group the 4 and the 2 together. That's where I get the 6. I can group the 1/2 and the 1/2 together. That's where I get the 1. 6 plus 1 is 7. Now, watch what happens here. 4.5 is still 4 plus a half. 2.5 is still 2 plus a half. But now, there's a time sign separating them. It's no longer a sequence of 4 things you're adding. You're multiplying the sum of 2 terms by another sum of 2 terms, and that involves the distributive property. And again, you might memorize this mechanically. Every term in the first set of parentheses has to multiply every term in the second set of parentheses. 4 times 2 is 8. 4 times a half times 4, half of 4 is 2. A half times 2, half of 2 is 1, and a half times a half is 1/4. So the correct answer is 8 plus 2 plus 1 plus 1/4. 8 plus 2 plus 1 is 11. The correct answer is 11 1/4. Now, it would be not put it in the wrong place here. The answer here was 7. That's okay. Now, there's no way of looking at this per se and seeing why this should be the right answer. But what we're saying is, even if I don't understand why this is the right answer, the rules of math tell me that it is. You see, everything that we're doing follows logically from our rules, and we accepted the rules because we believed that they were even self-evident. What was the one rule we picked in this course that we've really been utilizing all the time? That the number of tally marks in the group doesn't depend on the order in which they're arranged, okay, or the order in which they are counted, okay? Now, what is interesting is that this mechanical rule that may have looked mysterious becomes rather simple to understand if we use a geometry model, what we call the area model. And this is a nice thing to use because in the elementary school curriculum, you are working with geometric shapes, you're working with rectangles, you're working with areas and perimeters. This is a very nice application of showing how mathematical analysis can be visualized geometrically in many cases. I think I mentioned that before. If you look at the phrase, the number line, number is arithmetic, line is geometry. And what it says is points on a line, which we identify as being geometric, can name numbers, which is analytic. So let's see what happens if we use the area model. Instead of just thinking of 4.5 times 2.5, let's think of a rectangle whose dimensions are obtained as follows. You draw a 4-inch line and then a 1/2-inch line. Here you draw a 2-inch line and then a 1/2-inch line. So the dimensions of the rectangle are 4.5 by 2.5. Is that part pretty clear? But by one of the axioms of area, if you break a region up into constituent pieces, the whole area is equal to the sum of the areas of its constituent parts. Well, look at this piece over here is 2 by 4. That's going to give you, let me use a colored pen here. The 2 times 4 is going to give you 8. That's the area of this piece. This piece is what? It's 1/2 by 2. 2 times 1/2 is 1. There's where your 1 comes in. This piece here is 1/2 wide and 4 long, so it's 1/2 times 4. See, the height is 1/2, the base is 4. 1/2 times 4, it means 1/2 of 4. That's 2. And this piece is 1/2 by 1/2, which is 1/4. And so in terms of the area model, here's your answer. It's 11 and 1/4. You see, when you, and here's what's nice about this. The student who says, why can't I just multiply the 2 whole numbers and multiply the 2 fractions? Now the answer is, yes, you can. But when you do that and get the 8 and 1/4, all you found is this amount here. You still haven't factored in this piece and this piece. And what are you off by? You get 8 1/4. The correct answer we saw was 11 1/4. You're off by 3. And here's your 3. This is 2 by 1/2, and this is 1/2 by 2. This is 1 square unit. This is 2 square units. And there you have it. So now you have a visual way. Now, if you're really pragmatic and say, I don't care about geometry, I don't care about the rules of the math, I want something that works in the real world. So that's again where the adjective noun theme comes in. Let's personify 4.5 times 2.5. Let's assume that you're buying 2.5 pounds of candy at $4.50 a pound. That means $4.50 a pound. How do you find the total cost? It's the number of pounds times the cost per pound. So it's going to be 4.5, 2.5 times 4.5. But I can do this another way. If each pound costs $4.50, then 2 pounds is going to cost $4.50 twice. That's $9. And the 1/2 pound is going to cost half of $4.50. That's $2.25. So altogether, I'm paying 11 1/4. Remember when we took that estimate before, and we said that 2 times 4.5 is 9? Well, that was the part that it would have cost if it wasn't for this extra 1/2 pound. But that extra 1/2 pound costs you half of the $4.50. There's your $2.25. And there's your answer again, 11 1/4. And this is an example of what I call the nice versus the necessary. It might be nice if you could multiply the two whole numbers and the two fractions to get 8 1/4 in this case. But if you were the shopkeeper and somebody said to you, how much are you going to charge me for this $4.50 a pound candy if I buy 2.5 pounds? And you say, I'm going to charge you 8 1/4. You're not going to be in business very long. So it might be nice to multiply this way, but in the real world, it's necessary that we multiply the way we did. And again, if you wanted to do this thing mechanically, we can do the same thing we did when we were talking about adding and subtracting. You can rewrite each mixed number as an improper fraction, solve the problem as an improper fraction, and then convert the answer back to a mixed number. So what's another name for 4.5? Again, mechanically. 2 times 4 is 8, plus 1 is 9, over 2. 2 times 2 is 4, plus 1 is 5, over 2. We multiply across. 9 times 5 is 45. 2 times 2 is 4. The answer is 45 over 4. But that's if the noun is fourths. We want the answer to be in terms of whole numbers, so we have to divide the 45 by 4. 4 goes into 45. I shouldn't have to do this, but I don't mind doing it. The remainder of 1 means 1 of what it takes 4 of. There's the same 4 1/4 that you had before. And if you wanted to, you could even do this in terms of the area model again to see how does this relate to this. Remember originally what we had? We had the 4.5 times 2.5. Since the denominator is a 2 and 2 over here, let's assume that each cornbread is divided equally into 4 pieces. So you see this would be one. Let me see if I can show you that. I'll use I don't even know how these will show up. Let me use a brown one. See, now a cornbread is one of these guys. So see if you can follow me, okay? This is 1 cornbread, 2 cornbreads, 3 cornbreads. See, every 4 pieces makes a cornbread. 4 cornbreads, 5 cornbreads, 6 cornbreads, 7 cornbreads, 8 cornbreads. That's 8 so far. There's your 4 times 2 is 8. Now I have what? 4 more pieces gives me 9. 4 more pieces gives me 10. 4 more pieces gives me 11. And 1 piece gives me 1 of what it takes 4 of. So the answer is 11 1/4 again. And if this gets too complicated to draw, just refer to them. We'll change the nouns again. 4 would be the big square, and these tiny little ones, the ones that were divided into 4 equal parts, we'll call that a small square. So 4.5 big squares are 9 small squares. 2.5 big squares are 5 small squares. So now the area is what? 9 small squares times 5 small squares. That's 45 small squares, These should be squared, because you're also multiplying the unit, which doesn't really matter. And now since it takes 4 small squares to make 1 big square, the area again is 45 divided by 4. There's your 11 1/4 again. All these different ways to visualize the problem. Again, is there anything wrong with using the mechanical recipe? No. The wrong part is not to understand what it means. In fact, when you see a problem like 4.5 times 2.5, at least recognize that the answer has to be bigger than 8, because 4.5 is bigger than 4, and 2.5 is bigger than 2. On the other hand, 4.5 is less than 5, 2.5 is less than 3. So right away, before you even start this problem, you know that whatever the right answer is, it has to be bigger than 8, but smaller than 15. And I think this brings us to a nice place to come to our practice problem and wind up today's lecture. Again, I'm going to keep emphasizing this. I'm not trying to teach you to do anything new. I'm simply saying that I think if you can get yourself used to the cornbread concept, to the quantity versus number concept, you're going to find it easier to have your students internalize the basic recipes. They can still memorize them, but they'll see where they come from. And when you can understand where they come from, you can rederive them whenever you need to. It's when you memorize them and then you forget what the formula is. There's no way you can do things. Except now, thank goodness, there's something called the internet. And if push comes to shove, you can Google the problem, and sooner or later something comes up that tells you where you can find the answer. Anyway, let's do our practice problem and wind today up. And the practice problem, remember what you do. Pause the video, read the problem, and do it. Just to see if you've captured how to do the multiplication. Just compute the product, 3 3/4 times 2 2/5. Do it any way that you want. Do it as many different ways as you can, and then come back and watch how I did it, okay? One way to solve this problem is the old-fashioned way. Just convert each of the mixed numbers to an improper fraction, and then since we know how to multiply fractions, we'll just solve the mixed number problem as a fraction problem, and just get what the answer is, and we'll just see how it works out. So another name for 3 3/4, 4 times 3 is 12, plus 3 is 15. This would be 15/4, okay? 5 times 2 is 10, plus 2 is 12, so this would be 12/5. And now how do we multiply? We multiply numerators, multiply denominators. That would 15 times 12 gives me 180. 4 times 5 is 20. 180 over 20 means 180 divided by 20, so the answer is 9. By the way, since you multiply numerators and multiply denominators, it shouldn't make any difference if you reverse these. In other words, suppose I put the 15 over the 5 and the 12 over the 4. The problem now looks different, but wouldn't the answer still be the same? The difference is, do you all remember, I don't think I emphasized this, but I may have, that you can reduce fractions. Before you multiply, you can say 5 goes into 15 3 times, 4 goes into 12 3 times. So this becomes 3 times 3 is 9, over 1 times 1 is 1. And now you get the answer without having to mess around with big numbers. The justification for that comes from what we just did. You see, by doing this, the 15 over 5 is just another way of saying 3, and the 12 over 4 is just another way of saying 3. So the answer is 3 times 3. By the way, if by chance you wanted to do this problem without reverting to an improper fraction, what would you have to do again? The 3 would have to multiply the 2. The 3 would have to multiply the 2/5. The 3/4 would have to multiply the 2. The 3/4 would have to multiply the 2/5. When you get all through, the answer would still be 9, but it sure is a messy way to do it. Except if you use the area model, it's pretty easy to see. In other words, draw a length of 3 units, and then 3/4 of another unit. Draw a length of 2 units, and then 2/5 of another unit. So on the one hand, the area is 3 3/4 times 2 2/5. On the other hand, it's the sum of the areas of these 4 pieces. Well, the 2 times 3 gives me 6. This piece here is 3 by 2/5. 2/5 times 3 is 6/5. This piece here is 3/4 by 2. 2 times 3/4 is 6/4, which reduces to 3/2. And this piece over here is 2/5 by 3/4, which reduces to 3/10. In other words, it's 6/20 or 3/10. So now if we start with the 6 and we add on this piece plus this piece plus this piece, notice that the common denominator here is 10. 6/5 is the same as 12 over 10. Remember, 5 goes into 10 twice. 2 times 6 is 12. 3/2 is the same as 15/10. 3/10 is the same as 3/10. Now we have a common denominator, so we just add the numerators. 12 plus 15 is 27, plus 3 is 30. 30 over 10 is 3. The 3 plus the 6 gives me 9. There's another way of seeing it geometrically. Again, I don't know if you want to show this way or not, But for the student who says, I want to not use improper fractions, I want to do this purely in terms of mixed numbers, this is the way you have to visualize it. You need all four pieces. And if you're really pragmatic and you want the answer in terms of a real-world problem, pretend you were buying 3 3/4 pounds of something at $2.40 a pound. In other words, it's the number of pounds times the price per pound. So it's 3 3/4 pounds times 2 2/5, okay, dollars per pound. So what is the price? What price would you pay if you're buying 3 3/4 pounds at $2.40 a pound and you don't want to use mixed numbers? Well, you say, at $2.40 a pound, 3 pounds would have cost me 3 times $2.40. That's $7.20. At $2.40 a pound, a quarter of a pound would be 60 cents. And by the way, if the student doesn't like decimals, notice that $2.40 is 240 cents. So if the kid has trouble dividing 2.40 by 4, divide the whole number 240 by 4, but now the label is cents. So 1/4 of 240 is 60, and you're buying 3/4. 60 times 3 is 180. 180 what? 180 cents. That's $1.80. $7.20, $1.80. Added those up. There's your $9 again. The same answer that we got mechanically. So again, there are all these different ways of looking at the problem, but the unifying thread is that by using quantities instead of these abstract numbers, the students can begin to see why certain things are happening. And I've always maintained, and I've seen it happen in my own classes, that once the students can internalize the why, they no longer think of the how as being memorized, even though they do that. They can visualize what is actually happening when you're multiplying these two mixed numbers together. They can visualize a picture of the rectangle being divided. They can visualize buying so many pounds at so many dollars per pound. And at any rate, I think that's enough for today. I will look forward to seeing you again next time. And until next time, have fun, work hard, and I'm looking forward, as I said again, I'm just looking forward to seeing you again. Take care.